how do interlayer interactions influence interlayer exciton condensates, or something to that effect.
Thank you.
And there seems to be, I'll watch it for you. There's a dead zone there. I mean, there's a talking dead zone, so speak up.
Okay. But first of all, let me thank the organizer of this conference for inviting me here. However, I would like to thank in particular David Nilsson, a friend now for at least 20 years, who has been inspiring in the past and now work on bilayers. Okay, that has happened 10 and more years ago, and also today. So I will just be reporting about some work that we have been doing, motivated by what he has done together with Alex and Andrea. Let's see if it works. So this will be the outline, but it will not be followed closely, since there have been two talks today, one by Alex and one by David, already touching some of the things that I had prepared as background to motivate what we have been doing. I will focus just a bit on the existing quantum Monte Carlo simulation at t=0 for the louder shouting. Okay. The existing simulation, quantum simulation for the t=0 symmetric electron hole bilayer. Then I will say a few words about what we have already heard this morning by Alex and by David. Recall something about screen interaction, and then present our calculation and then conclusion. For all numerical aspects, you are directed to Stefania, who has done the solution of the self-consistent equation. So I don't need to say much about this picture. You have seen it so many times. The only thing that I can say is that because I have in mind contact with the simulation where parameters are defined in terms of single particle properties and not exciton, here you find numbers that are different by a factor 2 or so by what David presented today. So you have learned that in this coupled bilayers you can have quadratic dispersion, which allows you to make some contact with symmetric electron hole bilayer. And that's all for that, because we've already heard enough. This has been also covered, but let me say a few words. There has been a first paper in 2013 by the three guys that I will not mention by name anymore, because otherwise it will take too much of my voice and energy. And so the first calculation they did, together with a suggestion for systems that might be fabricated, even if the experimentalists of the group this morning had some words of caution about the fact that they will be realized. At least he says he will wait for other people realizing and fabricating them. This is what I understood. They also offered a theoretical analysis of the system by resorting to RPA screen interaction, and I will say more later on. And then, having found interesting results in this first paper, they tried to test the accuracy of the model scheme used for the coupled bilayer, graphene bilayers, by applying it to something for which there were independent, accurate results by Monte Carlo, the symmetric electron hole bilayer. Okay? Finding an apparent validation of their model. So let's go to Monte Carlo. Having this chairman today, I have to mention that I will be talking about two simulations. However, before these two simulations, there were two PhD students, one by Alan Anthony Chan, if I'm not wrong, and one by myself, Francesco Rapisada, who had done some preliminary calculations. Okay, but those that really so light are the two that I will be talking about. There are other simulations at finite temperature with path integral Monte Carlo. I will be focusing only on zero temperature diffusion Monte Carlo. So this is our 2002 investigation. You find the phase diagram here. Okay, we were trying to establish what would happen when you moved in the RS-D plane. Careful, this D is not in atomic unit, but is with reference to the natural distance in the layer, RSAB, because that gives an inverse coupling for the importance of the interlayer interaction that way. So you have two couplings. One is the RS, the in-layer, and this is the inverse coupling for the interlayer. Okay? And we found this phase diagram in a very crude way. Okay? This is what we could afford at the time. We were using three different wave functions, one for the plasma phase, one for the excitonic, one for the Wigner crystal, and we are just comparing the energies, and we would decide which phase was stable depending on which one had the lowest energy. You can realize that given the points that we calculated, which are those symbols there, okay, defining a boundary for the excitonic to plasma phase was not the easiest thing, okay, but we were brave and we did it anyway with the numbers that we had. We also evaluated some condensate fraction, 4 of them, okay. These are the BCS values, these are the variation of Monte Carlo, and these are fixed node extrapolated values. I will focus on those later on when I compare with more recent data. And here we come now, 11 years later, to the simulation by Nitsa and co-workers, first author of Maezono. What can I say? 11 years in the computers means a lot. So that makes the difference between our Hua main wave function and a wave function with 47 variational parameters. You can, I guess, fit in the universe more or less and more. Okay. So they have a unique wave function which describes all phases. They just optimize it variationally, okay. And the wave function has the flexibility to go from a plasma phase to an excitonic phase, not to resistor, I believe. And they also have explicit correlation to account for biexcom, something that we certainly did not put explicitly in our simulation. They also optimize the nodes to some extent, even if at the variational level, because they also have a flexible form for the pair function, which is also optimized. A technique that I believe goes back to Tarso, if I'm not wrong. So this is their phase diagram, but let's first look at these plots here, because we will be talking more or less about the condensate fraction all the time. So these are their condensate fraction at various RS's, at various distances. As you see, 11 years make the difference that you have all those points. We had 4. So what happens? Let's start at distance 0. Even at distance 0, you need a finite RS in order to get a finite condensate. Then, as RS increases, you go to a maximum, but then you go again to 0, and the excitonic phase disappears at large D. This is something that keeps going on as you increase the distance. Simply, the first boundary is moved slowly toward the right, while the second boundary moves much more on the right. Okay? Even if simulation are made up to 12, I believe, something like that, I'm sure that if you go much further, all those curves will turn down again, and I believe there are motivations to believe that. From these numbers, they can construct a phase diagram now. Here, the distance is in atomic units, so it's different from the phase diagram you saw before. This is the C equals 0 line. I won't be able to show it, okay, but you see it. It tells you the distance as function of RS at which the the condensate disappears if you start from here, or if you come that way, it gives you the RS at given distance at which the condensate appears. You can see clearly that the condensate disappears here. Okay, that's that part. So the condensate is in this region.
But in nanometers, I mean, if you want to put this one for distance like nanometers, what would be here?
Atomic unit means, well, this will, you have to take the parameter of your system, h bar is not, but m star, and the electric constant, construct your bore radius, and it will be in those units. So if you are, for instance, in gallium arsenide, the bore radius is 100 angstrom, that means that 1 is 100 angstrom, and so on and so forth. Okay?
For this variable graphene system there?
Bore radius is, in my units, is 4 something. Okay. Okay, so here is a comparison for the. No, I believe I got too far. Yeah. No, okay, sorry. This is the first comparison between our phase boundary and the new one. The only thing that I can say that by considering the way it was obtained, we can only be happy about the agreement. Let's instead look at the condensate. Here I have some, I do not agree with the statement which is contained the physical regulators, and I will substantiate my opposition to that statement with the facts. They say that our result for the condensate fraction, this is the Cambridge group, agree with those of reference 5, which is us, for large d, but we tend to obtain larger condensate fraction for small d. Now we had 4 values. One was at RS20, and they do not arrive at RS20. So we have 3 numbers on which to play it. That's very easy. At small distance, d equals 0,2, we are on the top of their point. Okay, that means that at small distance we agree. And at large distance, we tend to have a smaller condensate. So it's exactly the opposite of what they say. The problem might be due to errors due to the way you measure d, whether in atomic units or in terms of RSAB. Okay, so this is the full Hamiltonian of the system of 2 layers, 1 electron, 1 holes, okay, which interact both in plane and between the planes. And what the guys here have done is to replace that by an Hamiltonian with just 1 potential term, which is the interaction, a screen interaction between the electron and the holes. In this, again, here A and B refer to electrons and holes, so that we have creation of electrons and holes there. They use a BCS-like wave function, they minimize the expectation value of the free energy, and they get the solution. The results that I have are those published, and they are different from those that you have seen this morning, because there was a mismatch in the definition of RS between this work and the simulation. So that means that these boundaries, the red one, which was so interesting, move on the right by factor 1.4, which is the square root of 2. Okay, which means that still, I mean, this result, red, which is the superfluid screening result, still is possibly the closest to the Monte Carlo. But we will focus on this later on by presenting our simulations. So, screening. Let me say that that is a textbook exercise to get screening in a system of mobile charges. Okay, so I will not spend much on that. However, if you want to check the correctness of these 2 equations for the screen interaction for the electron and the electron hole, you can check a paper by the chairman, which is about 2 years old. He also doesn't give any derivation, just the equation. But we do not just copy the equation from the paper, we derived them, and we found exactly these 2 equations. That is what you do essentially. Okay? You connect the effective interaction to the bare ones through the inverse electric constant. The electric constant is written in terms of response functions. Response function are written in RPA. That's it. Okay? And then everybody knows RPA. You construct the polarizabilities, and that's the end of the story here. Phi n and phi a are the normal or diagonal. You have the interlayer. Okay, so it's the inlay essentially, and that is the normal. And the anomalous off diagonal is the term which appears when you have the matrix of the diagonal on the other terms. Okay. Of course, we are taking equal HH, so I will use only one. The normal screening is obtained when you put the anomalous term to 0 and the normal term to coincide with the two-dimensional linear function or step function. Yes?
Are those just all single species? I mean, pi n and pi a. It's single species?
Depends on what you put in. You can put, for instance, 4 components on each plane and you will have all 4 of them. Okay, this is not shown here, it will be shown later when I give the explicit expression of the guys, whatever you like. I have some comments about this business of screen interaction, and I'm very eager to hear the reaction of my child about that. Okay. Screen interaction, a common concept when you want to consider test charge, okay, interaction in a system of mobile charges. And if you do the electric treatment of systems and all that. To me, it's less far obvious that once you have got some effective interaction, there is a natural Hamiltonian in which you put them. Where, in fact, the business here, you take the bare kinetic energy and then you put an effective interaction. I must say, I did the calculation just for curiosity, out of curiosity to see what I get. But had I to justify it, I would be in trouble. I don't know how. I don't know if there is any systematic way where you start from an Hamiltonian, you do systematic approximation to the Hamiltonian, and you get out this kind of result. I don't know of any such technique. However, as a layman, I just try and see, okay, see what I get. And just for clarity, the electron hole effective interaction is this when you take all the terms. The one used by Andrea, Alex, and David is slightly modified as this form, and they are throwing away the electron-electron interaction. Now, when you go to the PCS treatment, you take the average of that Hamiltonian, you get this equation now. Sorry, this will be an effective Hamiltonian. Of course, all these are effective interaction. At the moment, I'm plugging all of them in there. Okay. Then you take the average on the usual PCS state, and you minimize. You see that now I have a sigma that can count both spin species and Wallis index, okay, if you like. That would be relevant only if you choose the situation in which in each layer you have a different population for the species. Then you will get different equation, different parameters, and different solution. But here we have restricted to the case in which if we have 4 components, that in each component we have n divided 4 as a density. They are all equal density. However, like this you can also do the spin polarized, value polarized, whatever you like. Of course, since we want to have to gain most of the energy by the interlayer, we will take identical polarization in the 2 layers and couple up with up, white with white, and so on and so forth, so that we can get the max. These are the anomalous and the normal guys, polarizabilities. And as you see again here, you may have the sum over spin if you have such asymmetry between species. This is all standard, so I will not pause on it. I must say about something. Look at this. Now consider a situation in which out of your self-consistent calculation the gap goes to 0. But you have retained the electron-electron interaction and the whole interaction. Okay? This guy here will not go to the Lindard. We'll go to a modified Lindard where the eigenvalues in the sum have exchanged. So some general observation about what we do. We solve the mean field equation iteratively. We account for the full k dependence of delta k. We start from a trial delta k, and then we go on iteratively. We start with a mu that puts us at larger s where things are easy, and we use the gap that we obtain for the next mu, which is very close to the one we started from, okay? And that gives us a branch of solution, as you will see. At each mu, we get the RS, of course, as output of the calculation. Now, what turns out that we find one solution with finite gap. I mean, a gap which is not exponentially small, or no solution with finite gap. If we start our iterative solution with a very, very small gap, typically we do converge, but with the same chemical potential, of course, that we use there, but at a different RS. Okay? That poses some problem about what you do with these solutions. And this is the statement that I already made about the screening and the limits of screening. So here are the results of the calculation. I apologize for the number of curves. I'll try to guide you among them, and if I do not succeed, it's my fault. So, these are the results of simulation, the balls. This is the condensate here. I'm just using a normal scale, okay? These are the Monte Carlo data, the way they are presented by the authors, and I present them like that. Of course, if you use a logarithmic scale, you enlarge a lot this point will go up there, and you have the impression of a drop. Okay. To me, this is a very smooth curve. Think of the minus cosine crossing the axis here, go perfectly to that. Okay. So, one thing is certain, it goes to zero. But I will not ever, even under torture, I will not speak of a jump. Okay? It goes to zero, but without any jump as far as I'm concerned. So this is, let's say that that's our reference. For the moment, we consider that as the truth, and we want to compare other things with it. These red curves are the bare interaction results, with all the interaction is the continuous red, and the dashed red is only with electron hole. You see that putting the in-plane interaction moves the result toward the more precise result. However, we have the gap that continues all the way to the origin. Now we go to the interesting part, which is the calculation with only the interlayer effective interaction. Using the form of the screening that I presented, which coincides with Alan, we get this blue dash. Okay? While if we use the one by the other authors, we get the black, and that should coincide with the results presented this morning, I believe. Now, we lose the solution here. Okay? So, I leave to you to decide how we interpret it. Okay? We have the solution, and here we have zero condensate. However, we are only looking at that big gap solution. Okay? Underlined here, there is always an exponentially gap solution. So, why I disregard that? I throw that away when I use the other solution. That's all for you, okay, to decide. If you put all the interaction, you get this full blue curve, which is over there. This here is the normal steering. It's clearly out of the picture. We can go to smaller distance. You see that these two, let's just focus on these two, the dashed blue and the black blue, tend to come together. You will see that at even smaller distance, they essentially coincide. So the difference in the interaction that we used become negligible. The other thing is that this curve tend to coincide until they leave with the simple unscreened interaction with all the interaction, which is the full red. Of course, the food bed continues nicely. And here is the smallest distance that we did, where this, see this dashed curve are almost on the top of the. Of course, however, here I use the solution, and this keeps going. There are strange things happening here, okay, on this solution. But this has nothing to do with the free solution that you find described in Allen paper or in Lozovic paper. They just have one parameter, and given mu, they plot the free energy as a function of delta over mu, and there are two minima and one maximum. Okay? At each mu we find just one solution, which will be, I believe, the big gap, which is the minimum big gap.
But you can calculate the energies of those phases.
I'm waiting for the calculation
okay.
to be produced, and that is what we will. I mean, my idea is that at this point, at given arrest, at given density, I will compare the ground state energies, okay, and decide what I have to do. That's certainly the way I see it. I'm happy that you also see it that way.
The collapse of the dashed curves from the red one means that doing the screening is irrelevant.
I'm sorry?
What you mean. So the fact that the dashed lines collapse on the red one means that doing or not doing the screening is irrelevant.
Not quite so, because the full red is bare with all interaction. And now it turns out that at a small distance, using only the electron hole with superconducting screening appears to give results that are superimposed to the full interaction, no screening. Again, there is plenty of surprises. I'm concerned, I do not have any deep understanding or explanation for them. Okay, we also did the calculation with 4 components, and now I'm really provoking you, because you see, I believe that you can't see these very, very light curves, which are how the food ones evolve when you go from 2 to 4 components. You will take my word, I will summarize what I find later on. And I have come to the conclusion, essentially, which are here. No, that's white page, and it's very nice conclusions. So, I believe it's clear enough that simulation indicate the disappearance of C at finite value of Rs, okay, at a given distance, of course. However, as I said, I will not speak of any jump, but of dying of that curve nicely. BCS type mean-field calculation produce results that depend on the kind of screening and interaction included. I believe that I showed all the curves together to emphasize that. And clearly, you can say, I take the one which is closer to the truth. How this will last when you move to a different problem, I can't guarantee, and I don't know. Okay. The superfluid screening with only the electron hole predicts a jump of the condensate to 0 at Rs somewhat larger than the one at which the C predicted by the MC vanishes, as you have seen. If one takes the scheme, this scheme, SS plus VH, as providing a reliable estimate or an upper bound to the Rs critical at which C vanishes, let me define this guy here, calculation with NC4 seems to indicate minor effects of the inlay value degeneracy, which comes as a surprise, because I believe that everybody would expect that it would help or would do something, but I mean, I can substantiate that a bit better. Look at, you see this curve here, the very, very light one, which is above the blue.
Yes.
That is the one with 4 components. It's higher, but dies earlier. Okay?
It's steeper. Higher, but yeah.
It goes up, but dies earlier. And here is upper and dies earlier. And here, what is it? The 3. Oh.
Okay.
And the 3 more or less is there. So it's not conclusive. The only thing I can say is that the simulations for the symmetric electron bilayer with valid degenerates are called for to understand something. That's my topic.
Okay, so additional discussion going
I
on.
have one question. In the DCS timing field, you know what sort of screening you're going to put in the system, because you're putting by hand. I did not understand what about the quantum Monte Carlo. Do you have a feeling of what sort of screening comes out?
You start from the Bayer interaction and you take the Bayer
So,
interaction.
because
There is no screening.
my feeling in this detailed timing field calculation, you put only the screening in the particle hole channel. Whereas when you're close to the crossover, you have to put also screening in the particle channel.
The crossover in which region?
I mean,
Where?
Well,
There?
you see, because when you, but the plasma frequency should, what is the plasma frequency in this screen?
Not.
Should be unchanged, whether you have
My
in terms of
summary
thermals
would
or
be
both.
that we already knew from the history of high temperature superconductivity theory that it's hard to give definitive theory for pairing due to electron-electron interactions. So, yeah. So I would tend to agree with Gaetano's final conclusion, actually, that those Monte Carlo calculations, which also have limitations,
Of course.
but are called.
The Arterios.
Yeah.
Forget it.
Okay, additional comments? Go ahead.
Yeah. So I would like to understand the role of spin. So especially the Monte Carlo calculations. So so if you have any hint of what would happen if you just consider instead of 4 components, just 2 components in the 2 layers, so fully polarized. Of course, this would change the equation of state.
It's the number of determinants that you put in your trial function. I mean, if you have polarized one component, you have one determinant. Okay,
No,
compare
this
function
is
and so on and so forth. This is, I mean, in practice, what you put in. So, what was the question then?
The question is, if you think that the results on the condensate fraction would completely change once you go from 4 to 2 components,
The Cambridge group has only done the unpolarized, as far as I remember. We did some check, some little check. We also did the calculation for the unpolarized, but we did some little check for the polarized space, which however was never stable with respect to the other calculation.
Frank?
Just a comment, I guess, on your comment, which, and following up on Giancarlo, I mean, if you repeat the quantum Monte Carlo, presumably you can also extract the vertices that should go into the pairing.
Vertices. You presume.
Well, this is the sort of the Santa Barbara group does this a lot with Hubbard-like models. You'll actually extract.
That's a totally different world.
It's a lot simpler.
There are many things that you do there that you can't do on the continuum.
But I have another question about this sort of variational wave function Monte Carlo. You know, in the real system, there are these 4 flavors, right? Spin and valley, and the pairing is probably, you know, which guys are pairing with which guys. That's part of the quantum fluctuations, and it's part of what suppresses.
So you're suggesting that one should
you build that in
allow
or
that
not?
to, I mean, that you, for y you pair with the down guy and get
My question was, is that something that can be accounted for or not?
Not in the wave function that I know of.
Okay.
Yes. Okay. It's funny because Cambridge group pairs up electrons with down poles. They are different particles, so yes. And if you want to polarize systems, you do the opposite. You do up and down, because then you have the mention of the third surface.
Exactly. Yeah, you know, everything's independent, of course.
That's very, very interesting what you asked. I personally thought that. Fantastic idea at the moment now I will do that.
Okay, so are there any more questions from anybody? I have a question. What's the score of the game?
So who's been watching?
Now they will confess.
Okay, thank you all very much, and thanks, Gaetano.